Let's talk about compilers. Until this point, you've just typed up your source code into some files, sent them through this big black box that is Clang, and out comes your executable file that does exactly what you wrote in your source code. As magical as that's been, we're going to take a closer look at what's actually happening when we compile a file. So, what does it mean to compile something? Well, in the most general sense, it just means transforming code written in one programming language to another. But usually when people say they compile something, they mean they're taking it from a higher level programming language to a lower level programming language. These may seem like very subjective terms. For example, you probably don't think of C as a high level programming language, but you do compile it. But it's all relative. As we'll see, the assembly code and eventually machine code that we compile down to is undeniably a lower level than C. Although we'll be using Clang in today's demonstration, a lot of the ideas here carry over to other compilers. For Clang, there are 4 major steps in the overall compilation. These are 1. Preprocessing, done by the preprocessor. 2. Compilation, done by the compiler. 3. Assembling, done by the assembler. And 4. Linking, done by the linker. It may be confusing that one of the substeps of the overall Clang compiler is called the compiler, but we'll get to that. We'll be using a simple Hello World program as our example throughout this video. Let's take a look. The first step is preprocessing. What does the preprocessor do? In pretty much every C program you've ever read or written, you've used lines of code that begin with a hash. I'll call it a hash, but you may also call it pounds, number sign, or sharp. Any such line is a preprocessor directive. You've probably seen hash define and hash include before, but there are several more that the preprocessor recognizes. Let's add a hash define to our Hello World example. Now let's run just the preprocessor on this file. By passing Clang the -E flag, you're instructing it to run just the preprocessor. Let's see what happens. It looks like Clang just spits out everything at the command line. In order to save all of this output to a new file called hello2.c, we'll append greater than hello2.c to our command. Now let's take a look at our preprocessed file. Whoa, what happened to our short little program? If we go all the way to the bottom of this file, we'll see some of the code that we actually wrote. Notice that the hash define is gone and all instances of name have been replaced with exactly what we specified in the hash define line. So what are all of these type defs and function declarations at the top of the file? Notice that the hash define wasn't the only preprocessor directive that we specified. We also have hash include standard.io.h. So all of the crazy lines are actually just standard.io.h copied and pasted into the top of this file. That's why header files are so useful for function declarations. Instead of needing to copy and paste all of the function declarations you plan on using at the top of your file, the preprocessor will copy and paste them from the header file for you. Now that we are done preprocessing, we move on to compilation. The reason we call this step compilation is because this is the step where Clang actually does its compiling from C to assembly code. In order to have Clang compile a file down to assembly, but continue no further, pass it the -S flag at the command line. Let's take a look at the assembly file that was outputted. It looks like quite a different language. Assembly code is very processor specific. In this case, since the CS50 appliance is running on a virtual x86 processor, this is x86 assembly code. Very few people write directly in assembly code these days, but every C program you ever write gets transformed down into assembly. Again, we call this step compiling the C into assembly, since we are going from a higher level to a lower level programming language. What makes assembly lower level than C? Well, in assembly, we are very limited in what we can do. There are no ifs, whiles, fors, or loops of any kind. But you can accomplish the same things that these control structures offer using the limited operations that assembly does provide. But to see just how low-level assembly really is, let's go one step further in our compilation, assembling. It's the assembler's job to transform the assembly code into object or machine code. Remember that the assembler does not output assembly. Rather, it takes in assembly and outputs machine code. Machine code is the actual ones and zeros that a CPU can understand, although we still have a tiny bit of work left before we can run our program. Let's assemble our assembly code by passing Clang the -C flag. Now let's see what's in the assembled file. Well, That doesn't help us very much. Remember that the machine code is the ones and zeros that your computer can understand. That doesn't mean it's easy for us to understand. So exactly how low level is assembly? It's nearly identical to object code. Going from assembly to object code is much more of a translation than a transformation, which is why one might not consider the assembler to do any actual compiling. In fact, it's pretty easy to manually translate from assembly to machine code. Looking at the assembly for a main function, that first line happens to correspond to hexadecimal 0x55. In binary, that's 1010101. The second line happens to correspond to hexadecimal 0x895, and the next 0x56. Given a relatively simple table, you could translate assembly into the code that machines can understand too. So there's one remaining step in compilation, which is linking. Linking combines a bunch of object files into one big file that you can actually execute. Linking is very system dependent, so the easiest way to get Clang to just link object files together is to call Clang on all the files that you want to link together. If you specify .o files, then it won't need to reprocess, compile, and assemble all of your source code. Let's throw a math function into our file so we have something to link in. Now, let's compile it back down to object code and call Clang on it. Oops, since we included a math function, we need to link in the math library with -lm. If we wanted to link together a bunch of .o files that we wrote on our own, we would just specify them all at the command line. The restriction is that only one of these files must actually specify a main function, or else the resulting executable wouldn't know where to start running your code. What's the difference between specifying a file to link in with -l and just specifying the file directly? Nothing. It's just that Clang happens to know exactly what file something like -lm happens to refer to. If you knew that file yourself, you could specify it explicitly. Just remember that all -l flags have to come at the end of your Clang command. And that's all there is to it. When you just run Clang on some files, this is what it's actually doing. My name is Rob Bowden, and this is CS50.